Hey everybody, Evan here back again with another video for dynamic process and controls. In today's video, we'll be talking about a constant stirring tank reactor. So constant, basically how it works, a CSTR, is basically how it works is you have a liquid going into a tank. Well, we can say the tank is sealed. It can be open or closed, but in this process will be sealed, have a constant pressure. This will be sealed and a liquid will go flowing into the tank. Once it builds up, the tank will start mixing in. And on the bottom, we have a cooling liquid coming into it. Call this TC, a cooling liquid going into the tank. That's lower than the initial temperature going into the tank. A T in or T initial. I'll say T initial. T initial going into the tank. And it makes it so that once it starts reacting, the chemical gets to a point where it reacts with the constant stirring and the coolant of the temperature, and it produces a species for the product with a mixture of the components. So if we had a reaction, I'll explain everything right. So if we had species A going into the tank at a constant flow, because it's a continuous process, constant flow going in. It gets put into the tank, it stirs, it builds up, the tank builds up, it starts stirring. It's the mixture, the heated liquid gets cools down by the coolant liquid at the bottom. It's not going into the tank, but there's a transfer of heat in between the two layers, which then you start to see the reaction. And then the product comes out and they'll have a mixture of A and B. So you produce A from B. You produce B from A, sorry. So this is basically how it works. It's a continuous process, so it's a constant flow going in and out. This is our steady state. It's a constant flow. So the flow in and out are equal to each other. Okay. We know the coolant temperature is also constant at this time. So this is its TC throughout the whole entire process. We do have a temperature change coming here from entering it, and there's a change from the temperature exiting it, because of course it will be small, it will be cooler due to the change. Due to the coolant temperature changing the degree inside the tank. And then we also have a change in our concentrations of species A. Because like I mentioned, you need species A to produce species B. So some of the species A will get dissolved over time to produce the species of B, but some will still be left in the mixture at the end for the product, okay? So what we now know, we have our knowns, we have our known is that there's also, I'm gonna say that the volume is also constant. The volume inside the tank is constant, as the tank does not expand or contract during this reaction. So we know that we have for our known constants. Let me put it here. Constants. We know that our flow is constant, cooling temperature is constant, our volume of the tank is constant. And that's pretty much it. Our non-constants are unknowns. That we don't know the final temperature, the product temperature. I'll say it like that. We don't know our product temperature or the reaction, and we don't know the end concentration. You see concentration. species B, species A. Okay, so these are the two things that we do need to find for this reaction. And the courses be over a change of time because the reaction doesn't happen instantaneously. It will happen over a span of time. So we will need to find the change in temperature over a change of time. And we need to find the change of concentration of species A over a change of time. Okay. So these are our two unknowns that we do need to find. Okay. All right, so now we know our unknowns. How we find these? Okay, so we can use what we always have to use for all. That will solve most problems. Is a mass balance. Okay, we need to have a mass energy balance to find both of these unknowns. Okay, so again, let me say out what a energy balance is. So energy balance is well, I say mass balance for this. The mass energy balance. Mass or energy balance is the accumulation of product, what we're trying to find. Accumulation product of the reaction. So whatever accumulates, whatever gets produced, is equal to whatever goes in to the system minus everything leaving the system minus the desorption over anything in desorbed or that desorbed from the reaction, and then plus anything getting generated from the reaction. Okay. Let me make this bigger. I don't know if y'all can see it. Let me make it bigger. So. Accumulation equal to N minus out minus desorption plus generation. You see that? Perfect. Yeah, you see. Okay. So let's find our concentration first, because this will be a little bit easier equation than the change of temperature. Okay. So we will be using a mole balance for this. So let's see, mole balance. Okay. And for our accumulation term, we'll use the change in concentration divided by change in time. So again, our final product here. And then we will represent this also by volume. So we have how much concentration we have left of species A and how much volume is of the species A is left. Okay. So that's our accumulation term. We'll set this equal to what's going in. So we have a flow in, constant flow in. So it'll be Q. And remember the Q in is equal to our Q out. So we have so both our in and out, we can say our Q times. And then for each one, we have a concentration going in, a concentration going out. Okay, so that'd be our difference. We'll set that difference here. So we have Ca, initial concentration of species A minus final concentration of species A. And now let's set our in and out terms for both of these. So this is our in. And there's a concentration of A going in and then concentration of A going out. Okay. And then next, desorption. We do have a deterioration of species A over time, which produces B. So we have to have a loss of A to then produce B. So we will say, like if we remember, if you have taken reactions, you know that for our reaction, I'll say here, for our R, if we use this for our reaction, or say no reaction, that we represent this as for our reaction is equal to the rate of reaction, K, times the concentration of your species, okay? This unit here is representing to our rate of deterioration, rate of desorption. Which we can use the Argonaut's, pretty sure I'm saying that right. I'm reserving that. Argonaut's equation. Argonaut's equation. Which basically states that, okay, it's equal to the Argonaut's number times the exponential of negative E, which is activation energy, divided by our gas constant, which is usually represented as 8.314, and then times our temperature, okay? So this is what K represents for this, okay? And then we have our concentration A. So you will state this as, and this would be our initial for this chance, for this. And then we will need to multiply this again by what's the volume, okay? All right. So now we have this, we have the volume of the liquid, we have rate of absorption times the concentration of the initial concentration of species A times the volume of the liquid going in. We stated here, we can put this equation up here. Okay. And we will get, and then we can put that here, K times CA initial times volume, okay? And now last we have generation. We did not generate any moles here. We just used the moles that we had. From A to reduce B, we didn't generate more moles, but we did lose moles from A. So we don't need a generation for mole pounds, okay? So now let's just simplify this to get dCA divided by dt, the change in concentration of A, respective time by itself. So we divide this by volume. So formula by volume, and this will give us change the concentration of A times change of time, divided by change of time. It's equal to flow divided by volume times concentration of initial A minus the final concentration of A minus the rate of reaction, rate of desorption times our concentration, initial concentration of A. Okay. And here is our equation for the change the concentration of it. All right, so we already have one of our things checked off. We already have, and we already have this. Already have one of our unknowns found. Now we need to find the change in temperature. Okay. All right, let me erase this line. And for this, the final change temperature, we'd be using an energy balance this time. Okay. So let's say energy balance. Energy balance. Okay. So again, so let's start with using the math balance formula we have up top. Accumulation. So we know that our accumulation is, let me put it here, it's kind of very clear. Change in temperature, expected time. Okay. Now we know flowing in, we have the density, we know going in for this, it will not be the same as this. We will have to use so let me say this right. Okay. Basically, for our liquid going in, the liquid has a certain amount of density. Okay. So we know that for our accumulation, we have a specific amount of density from our liquid that we need to use. That we'll have at the end. We still have a volume. So volume. So this we have a density of the liquid times the volume. And then times the specific heat of the liquid. Okay, so for our accumulation, we'll have, it'll be the change in temperature, expected time, times the density of the liquid times the density of the volume. Is that, no, is the volume of the system. Yes, so we have the density of the liquid times the volume of the system, and then times the specific heat of the liquid, okay? Yes, right. Yes, yes, you got the volume of the flow going in, yes, the volume of the pipe going in, yes, okay, makes sense. Yes, so this would be your accumulation for for energy balance, okay? We'll set this equal to, let's do in and out. Okay, again, we know that we have a flow, we will have a flow. So we have our flows are equal, so Q times, again, density. And then, let me see, is that correct? No. So for going in, we still need a volume. That's correct. We still need a volume. We still need the flow going into the system, so Q. And then we also need the density of the liquid, yes. Okay. And then we'll represent this as T going in, your initial temperature, minus our final temperature. Okay. All right. Next, we'll have our desorption. We do have a desorption. It'll be the desorption of the heat lost. So, no, it'll be desorption of, yes, the desorption of the heat being left from the, let me explain this better. So, the desorption will be the change of heat, the decrease in heat, the desorption of the energy of heat being transferred in from the cooling liquid from our liquid coming from the top. So it's the transfer of heat or the loss of heat here from the bottom and like all around the system, which would be the desorption of the energy basically of our heat. So we'll put that as a desorption of heat, which we'll put as our heat transfer coefficient, which we represent as U. And then we'll times that by our area. So the area of the area of the cooling of the cooling area where this transfer is taking place. So this line right here. So it's the area of the transfer taking place. So all this right here. Okay. And then this will set this to the temperature of the system minus the temperature of the cooling liquid. Okay. And then lastly, generation. Now we are creating energy. Yes, we are. With the transfer, well, we are creating energy with the transfer. So even though there's a loss of heat, there is still a generation of energy. So we need to represent this by first having, again, you will have, what was it? This would be, let me think. This will be, sure. And then that'll be the volume times, no. It'd be specific heat. Actually, no. That's okay. I remember now. So yes, it'll be, we'll take this equation here again. So it'll be K times concentration of A times volume with respect to the change in enthalpy. Okay. Yes, that's the correct thing. So yes, so we'll multiply the generation of our, what is it basically? Of the, it's a negative generation from our negative enthalpy, but it's the change, it's a generation of energy, basically, from the moles, from the reaction. So we will be generating energy from the reaction, just dissipating. It is, okay, let me say it's better. Due to the reaction, we are, even though we are losing species of A, we are still generating energy from this. So we are generating energy, which we're gonna use our reaction equation that we already have. And we'll set this multiplied by the change in entropy to represent the change in energy, the generation of energy that we have in the system. Okay. So this is the energy balance equation. Let me check this real quick because I may have made a mistake. Okay, so I did just look at my notes and there was a mistake. It was the only mistake I made, which is when we are first initial in and out. So instead of volume, this would be the specific heat of the two liquids. It actually makes more sense. It wouldn't be the volume going in, but it's the, let me write this better too, because it looks like. So we will have, again, we have the flows of both the liquids, of the, what's the flow going in and out, and the densities of both the liquids going in and out, and then we'll have the specific heat capacity of both the liquids, and they should be equal to each other. So this is why we'll state this all the same here, and then this be times the temperature, initial temperature minus the final temperature. Okay. Now we have our energy balance for the system. Okay. If you want the change in temperature by itself, divide the left-hand side by the right-hand side, so the density divided by the volume times the concentration, I mean the specific heat. And then we will get a formula that looks like the change in temperature divided by change in time is equal to, it's not cancels out, it's not cancel out. The flows of both in and out, the flow of the liquid divided by the volume going in, the volume times temperature, initial temperature minus final temperature minus the transfer heat coefficient times area divided by density times volume times specific heat times the temperature of the system minus the cooling temperature, and plus our plus the rate of reaction times the concentration of A divided by the density times specific heat, and that'll be times the change of enthalpy with the negative sign. Okay. So here is our equation. Here is our equation for the change in temperature for the liquids. Okay. All right. So now these are our two equations that we have that we derived for the CSTR. And now the next step is that we'll put this into Python and we will get a mathematic and graphic of how this looks. Okay. All right. I'll see you guys on the next part.
Hi everybody, this is Evan again, back with the part 2 for the constant stirring tank reactor problem. If you remember in the first part, when we derived on the whiteboard, we wrote down and described what the CSTR is and how we able to derive the change in concentration and change in temperature as a reaction goes on in the CSTR. Okay. And now for this Python part, we just put everything, all the equations, all we stated on the whiteboard onto Python, and we'll be finding out the mathematical values for our given prompt. and graphing it to see how the graph oscillates over a period of time. Okay. So for our prompt, it asks us to derive the time-dependent material. They derive the time-dependent material and energy balance equations of the CSTR described. Encode, solve, and plot the time-dependent concentration and temperature profiles for the CSTR when the cooling temperature TC is at 305 kelvins at time equal to 0. Okay, so the initial concentrations that I already have put on the Python, but I'll say it out loud again, is that our flow into the tank, our flow is equal to 100 liters per minute. Our initial concentration is equal to 1 mole per liter. Our concentration going into the system is 1 mole per liter. The temperature going into the system is 350 degrees Kelvin. Our volume of the system is 100 liters. Our density of the liquid in general is 1,000 grams per liter. Our specific heat capacity is 0.239 joules per gram Kelvin. Our entropy is 5 times 10 to the 4th joules per mole. Our activation energy divided by our gas constant ratio is 8,750 degrees Kelvin. Our Arenos initial constant is 7.2 times 10 to the negative 1 inverse minutes. And then our transfer heat energy coefficient times our area is equal to 5 times 10 to the 4th joules per minute Kelvin. And then RTC, we are not be using the one that's stated here, but we're using 305 Kelvin. And then for the initial concentration at times equal to 0 is 0.5 moles per liter. And then temperature at times equal to 0 equal to 350 Kelvin. Okay. So now we stated that, let's start coding. Okay. So first let's define our function. So we would define, here's all the equations we use. It's going to be pretty quick and simple code. So let's just plot this out real quick. Okay. Let's start with defining our function. We start with the same right-hand side. So define right-hand side. And we will just put this as the time into our vector that we're defining. Okay. So respect to time in our vector. Okay. And then in this function, our vector will be equal to our temperature and our concentration. Okay. So that's what our vector is equal to. All right. Now we have that stated. Let's first put in our Arenos equation. I hope I'm saying this right. I hope I'm saying it right, but let's put in our equation so then we can put in our change the concentration and change the temperature because we need this bad boy here to calculate both of these. Okay, so let's put this in first. So that K is equal to that our Aronoff. K is equal to our Aronoff constant times MP the exponential of negative, don't forget the negative, activation energy times our reaction, our gas constant, and then we divide this by our temperature. Okay. And this will be the temperature respect to our function. Okay. All right. Next, let's start this. We can start with our concentration. So we are trying to find our change in concentration. Okay, so CA. We're gonna take this equation and put it in the Python just like that. So we'll do dCA is equal to, and we don't want to put in the divided by dt because we're already saying our function that is in respect to time. Okay. So let's put this in. So we have our flow divided by the volume of the system times the concentration, initial concentration, C A0 minus C, which is from the function, and then minus K of C times C, again from the function that we have. Okay. Next, we will put in our change in temperature. So dT, and this equal to flow divided by our volume, and then times, let me put times here, forgot that as well, but times our change in initial temperature minus our final temperature, which would be finding. Then we set this minus our heat transfer coefficient times the area, so UA, times our temperature minus the coolant temperature. So we know from our prompt that is 305, so 305 Kelvin. Let me say here, 305 Kelvin, and then we'll divide this all by our density, which we have stated as rho, times our specific heat, and times our volume. Okay. And then lastly, we'll put in our Aronofsky constant times our concentration of A, so C. And then actually, would this be C or be CAI? I think it would be CAI. No, it'd be initial concentration. CA0. Yes, I'll check that later, but I'm pretty sure that's right. And then times our negative entropy. So we have that stated as neg HR, then divided by rho times specific heat. Okay. So let's return this. Return dCA and dt. Okay. Shift enter. Well, I need shift enter everything. Shift enter, shift enter, shift enter. How'd that work without OK? All right. So now now we need to put it into a solver. Okay, so we want to put our function into a solver so we can have this can run correctly. Okay. So, and again, we'll be using, like we did for our last controls, we'll be using Radu for our method for our solver. Okay. So we need a time component to see how long our solver run for. So, and I think it says it in it does not. Okay. We'll run this for this 10 minutes then. So we'll say 10 speed minutes. Okay. And then we'll do solve IVP. Excuse me, I need a tissue real quick. I'll be right back. Okay, I am back. All right, so now let's put in our function IVP, solve IVP. So let's right hand side. Next, we'll put our T-span. So we'll put this as 0. And then to tend. All right. Next, we'll put in our initial guesses. So that will be our T initial at times 0. So our T0 and our C A0. Okay. Then let's put in our method. Which this is equal to Radu, like I said earlier. And then we need to do a dense output because this is a continuous function and a continuous system. So we need to say our dense output is false. Did that correctly. Is dense output. So now how you state it? I'm pretty sure it's how you Oh, is it because it's not a capital? It is. I was like, what? Okay. Now we should be good. Should enter. And it works perfectly. Okay, so now let's put this into a plot. So this is our value. So you see our temperature change. We have our, where is it? Our time on here. And then this is our, this line here is our change in temperature. And this one here is our change in concentration. Okay. So now we have that. Let's put this into a graph and see this on a, let's see this on a graph. Okay. So I'll say this as is equal to res. So our results, not that. Res. Okay. We know how to graph this. Okay. So first we need a time for our x-axis. We need a time axis. So t plot is equal to np land space. We do 0, comma 10. Let's do 200. And then our y-axis, this will be our x-axis, and our y-axis will be our time plots, temperature plot, and our concentration plot, which should be equal to res dot solve t plots, respect of our time plots. Okay. All right. So now let's make a plot. So fig make subplots. No, fig dot make subplots. Make subplots. There we go. I'm tweaking. Let's do it on one day. Next, I make subplots, and then we also need to input before we put this, we need to input our rows and columns because for this we want to have two graphs side by side. So we need rows, which is be equal to one row. So it'll be on one row, but we need two columns for the row. And then columns equal to one, equal to two. Yeah, that's right. Okay. All right. And then fig dot add scatter and x is equal to t plot. Y is equal to t plot. And then our name is equal to temperature. So our x-axis is equal to our time plot, and our y-axis equal to our temperature plot. Our name is equal to temperature, and I forgot to add our rows. So we need to have rows, row is equal to row 1, and then columns equal to 1. Okay. Now let's add our concentration line, concentration graph. So x plot, x is equal to t plot, y is equal to concentration plot, row is equal to 1, and then our column now for this one equal to 2, and our name for this would be equal to concentration. All right. So now let's do our layout. So fig update layout and width, no height. It's equal to, let's say, 500 width. It's equal to 600. We have two graphs, so let's say 600. And then template, last thing, it's equal to poly dark. All right. And now let's shift enter. Res is not defined. Non-type. That should be uh, non-type object. Non-type object is not calculated and callable. T plot, C plot. Why can we not call this? Explain error. What's wrong? Why is when you try to call object that is none? In this case, the error occurs in the case that is none, which likely means that. Hmm. So it's saying that since we have our dense output as false, it will come up to that our solver can't run. I mean, it will say that it's none. That's weird. It needs to be false. So why is it? Let me look at my notes real quick, and then I'll be right back. Okay, I just checked. I made the mistake. It's supposed to be true, now false. So this, when I say they're false, it didn't even change nothing. It's basically still saying that it's not a continuous process, so it's false, but it needs to be true. As this is a continuous process, it doesn't stop. So this is true. Fig is not defined. This is why I'm making subplots, though, right? What? Fig. Oh yeah. Fig is equal to make subplots. Make. That's why. Thank you. Okay. That's why I forgot to put the equal sign. Okay. I think we should be good now. In columns equal to 2. And then shift enter. Well, okay. Um, the oscillations are good, but I don't think this is particularly right. Um, yeah, I think this is oscillating way too much. It's supposed to, yeah, it shouldn't be going back up to 350 and coming back down. It should be kind of in the middle. Is that to probably have to do with my equation then. So let me say, I think it is this. I think this was the problem. I think this needs to be CI. Try this again. That was not the problem. Let me see. Must contain. Let me save this C. Hmm. So we have change. Yeah, that's correct. And we have our change of concentration, Q times V, divided by V times central concentration minus concentration, fine. And then times our concentration line. I do know that this is wrong in our paper. It should be final concentration. So I'm not looking at that right now. Um, but then our concentration should be, let me try that. Maybe that's the reason why the initial. I was going over that, so I know that's incorrect. Okay. Let me go back to this A to this C. Hmm. Change the temperature. This looks correct, so I am kind of confused. What's the problem here? K times CA times a negative integer, negative entropy. Let's see if it's because I returned T and C instead of that didn't make it. That made it worse. Okay, I'm gonna be right back. I'm gonna figure out what's the problem here. I'm pretty sure it has to do with my equation or whatever I'm returning. My equations look correct, but I think what I'm returning is incorrect. So let me check what I'm returning real quick, and then I'll be right back. Okay, I'm back. I just looked at my notes. Okay, and there's a few things that I've noticed I was wrong. So we got our concert. So the concentration thing was the thing I was messing us up. So for our change in the change in concentration, it needs to be has to be the CAI was going in minus out, not the I times zero, but what's ever going in minus the C we're taking. Okay. The next thing is that the initial concentration here needs to just be times the concentration fine. Okay, like I said earlier. So I was correct on that part. I also think you need to put this in the parentheses, if I'm not mistaken. And that should be everything I caught. I'm pretty sure everything else should work. Let me try this now. Hmm. Oh, also last thing, I'm sorry. This I was correct also. So this needs to be the change in temperature change of concentration, not just what we're spending for our function into. So let's try this now. Perfect. Yep. All right. So now as you see here, this is correct. I'm pretty sure. Um, I know my concentration is correct. So yes, it starts off high. It decreases and it increases, decreases and increases. So as reaction goes on, the concentration will increase to a certain point, and then it will decrease in concentration for species A. It just depends on how much flows in. I mean, due to the temperature, depending on the temperature, but the temperature, this doesn't seem correct. I'm pretty sure it should be looking like this graph. What is the problem? Why is this not cooperating? UA times yes, rho times yes, plus this should be correct. I may be messing up. No, I think this is the correct graph. I'm pretty sure this should be correct. I'm gonna check one last time. I'm sorry to have all these stops, but I do believe, I know our concentration is correct. I just want to make sure our temperature is correct. I just don't want to give you guys the wrong graphs for this presentation. So I'll be right back for the last time. Okay. I checked my notes last time. I was correct. Okay, this is the correct graph. So as we input our temperature in, we set it at 350. As a reaction goes on, the temperature will increase because the reaction is going on, it's producing energy. And then at a certain point, it will reach a certain point. Or as you see here, when it reaches a certain point at the highest temperature of the reaction, it then drops. Reaction reaction drops and it goes all the way to the point here around 362. Well, then and then it starts back up again. So basically, it's saying that it reached a certain amount of point to where the max going in at the initial time zero, that it the reaction got to a point where it got to the reaction A was done, and they used all of A to create B. So then it dropped back down until it had enough, the flow had enough A to then start reacting again. And then it kept going into units a cycle, and it followed as concentration. So then, okay, so that is the graphs for the two temperature and concentration graphs. I can widen it out more. I think that's what making it always getting me confused because it looked too bunched up. But yeah, this is the correct graphs for temperature, the change in temperature and change in concentration for a CSTR graph, for a CSTR reaction. Okay. Hopefully that helped. I know I was a little bit everywhere today, but this is the correct code. Um yeah, I hope this helped you guys and you followed along pretty simple and easily. I know I didn't make it easy, but I will see you guys in the next video. See you guys later.